Hi, welcome to this lesson on finance, present value annuities. Let's start off by looking at what is a present value annuity. So just like we did future value annuities, present value annuities have their own definition. So a present value annuity, as the name suggests, is a plan to pay back an amount of money that you borrow by making regular payments into an account that will accrue interest over time. So some examples of present value annuities include taking out a loan or taking out a bond for your home or your vehicle, whatever that personal loan might be for, and paying back that loan regular installments based on the interest that that loan amount will have accrued over time. We can calculate how much money we will be paying each month to pay back a certain amount that we borrow. Let us analyze an example to see how we can derive the present value annuity formula. So the key difference between future value and present value annuities is that future value is asking how much do you need to be saving up for each month and letting that money accrue interest over time to have a certain future value, a value in the future. Whereas present value asks us in the present, how much money do you have to pay back in equal installments if you borrow some money in the present time right now? That money will obviously have an interest rate attached to it. So when banks lend out money, they usually lend out what they call a prime lending rate or some sort of interest rate, which they will charge the money that you have borrowed from them. And that will be charged on top of the money you borrowed. So it'll be a higher amount. And then that amount gets worked out into equal installments over some time period. So let's have a look at this example. Kenny needs to withdraw 1,000 Rand from his bank account every year for the next 4 years. How much must he deposit into his account now, which earns 10% per annum, to be able to make these withdrawals in the future? We will assume that these are the only withdrawals and that there are no bank charges on his account. So let's have a look at the solution. We recall the compound interest formula. The accumulated amount, the amount you will have after depositing a principal amount with an interest rate and a time period compounded. So we are interested in calculating our yearly payments, the principal amount P. The interest rate here is given as 10%, so 0.1, and that is the effective interest rate because we are dealing with an annual interest rate over annual time. Okay, N is 4 years here, and the accumulated amount is the 1,000 Rand that Kenny would like to have in his account to withdraw each year for 4 years. Okay, so we can solve for P, that principal amount, how much we need to put in to get the 1,000 Rand, by making it the subject of the equation. So from here, if I solve for P, I will just divide both sides by this term, 1 plus I to the power N. So I have this equation here. So another way of rewriting this as a negative exponent is just bringing the base up to the top here and then rewriting the exponent as a negative exponent. Okay, so we first determine how much Kenny must deposit for the first withdrawal. So the first 1,000 Rand he wants to take out. So that's going to be how much he needs to put in to get 1,000 Rand over that space of the first withdrawal. So N is 1 here, so minus 1. And we see he has to put 909 Rand and 9 cents. So we can then repeat this calculation to determine how much he must deposit for the second and the third withdrawal. So remember, he's making 4 withdrawals over 4 years. Okay, for the second withdrawal, again, that's N equals 2. We'll substitute it into that formula that we had for P, which was A times 1 plus I to the negative N. That was just rearranging the old formula that we had. For the third withdrawal, we'll have negative 3, and for the fourth withdrawal, we'll have negative 4. Notice as we are going along each withdrawal, the amount that you have to deposit is getting smaller and smaller. So the deposit required gets smaller and smaller because it'll be in the bank account for longer and therefore earn more interest. So for example, here negative 4, that means if I put 683 Rand and wait 4 years, then I will have accrued interest enough to have that 1,000 Rand. Whereas if I'm only waiting 2 years, I would need to put a higher amount, 826 Rand and 45 cents, in order for that money to get to 1,000 Rand in 2 years' time. So the total amount that Kenny needs to end up depositing is essentially the sum of those 4. And that gives you 3,169 Rand and 86 cents. So all this calculation, let's put it into context of the problem. What were we actually solving here? So we construct a timeline to visualize the process. So we have T0, T1, T2, T3, and T4. And notice this makes up the 1, 2, 3, 4-year periods. Okay, so how we read this is immediately here, Kenny has to put 683 Rand and 1 cent into the account over 1, 2, 3, 4 years. At that 4th year, he will have accrued 1,000 Rand, which he can then draw out at that 4th year, or in the 1st year after taking an amount. Then 751 Rand and 31 cents is what he would have to put at the next year, right? And then that will accrue over 1, 2, 3 periods, and that'll give you the second 1,000 that you can withdraw. And then similarly here, for the third payment you're going to make, it's going to be that, and it's going to accrue over 2 years, and you'll get your 1,000 Rand back. And then similarly, if you're waiting and you're only putting in for 1 year, you'll have to put 909 Rand and 9 cents. And then after 1 year, at that interest rate, you'll have the 1,000 Rand that you can withdraw. So these are the 4 1,000 Rand amounts that Kenny needs to withdraw every year. In order to do that, he needs to put a sum total of all these payments together. So when we sum those payments, we get the 3,169 Rand 86 cents. So when he first goes to the bank, he's going to put that total amount into the bank immediately. That's the initial deposit. Then the amount after the first year that he'll have, so if it accrues interest over 1 year, that's just going to be, remember the formula, accumulated amount is the principal amount, 1 plus I to the n. So we sort of work backwards to get the principal amounts, how much he needs to be putting in, and then that total, let's see if it carries through. So now, n is 1 here, so after 1 year, the interest, remember, was 10% per annum. He will have put in the initial amount of 3,169 Rand 86 cents for a year, and he'll end up with this amount, 3,486.85. That is what he has after the first year. He's then going to withdraw 1,000 Rand from that amount, so minus 1,000. And he now is left with 2,486.85 in the bank account. Now that money is going to be sitting again for another year. So after 2 years' time now, so again, just after 1 more year, so that's 1 year plus another year, that's 2 years in total. That would have grown to 2,735.53. And again, after that second year, he's going to withdraw another 1,000 Rand. And now that leaves him with 1,735.53 in the bank account. That 1,735.53 is going to accrue interest over another 1 year period. So in total, it's been 3 years now, right? The amount after 3 years. So that amount's going to grow again by 10% for 1 year. And that's what he's going to have in the 4th year now, 1,909 and 8 cents. He's going to subtract 1,000 Rand from that because he's withdrawing again. So there's the third 1,000 Rand that he withdraws. And now he's left with 909 Rand and 8 cents. Now that is how much money he has after the 4th year. Then off from that 4th year, it's going to accrue, well, the 3rd year, sorry, after the 3rd year, then to the 4th year, it's going to accrue 1 more year. So that's that last interest payment there. And that's going to be 1,000 Rand that money grows to. And then he's going to finally withdraw that final 1,000 Rand and he has 0 Rand left. So essentially what this table summarizes is that if you want to know presently, if you want to have a certain amount taking away essentially, how much you're essentially paying back, we need to be able to work backwards with the compound formula, find that total principal amount, and then redistribute it out. So we're actually going to generalize this procedure, and this is going to give us the present value formula. So again, we talk about the geometric sequence formulae. Again, when r is greater than 1, we actually use this for the future value formula. But we're actually going to use this one here for the present value formula. And we're going to see why now, because our r value is going to be less than 1. Okay. In the practice problem we just did now with Kenny's deposits, that principal amount that we needed was the sum of these amounts, these 4 amounts here. But these 4 amounts were essentially the 1,000 Rand, that amount that you are essentially, that Kenny withdrew. And then that accrued interest, right? But then we had the negative sign because we rearranged the formula. So remember we had a equals p plus p into 1 plus I to the n. So therefore, if we solve for p, it became a times 1 plus I to the negative n. So that 1,000 Rand was that accrued amount, or the accumulated amount rather, that we wanted to have. in order to determine the principal amount, how much we need to be depositing to get that accumulated amount, we had to use this formula here. Okay, that's over the 1 year, then the 2 years, the 3 years, and the 4 years. Again, notice the 4 years, the least amount of money with the 4 years, because that has 4 years to attain interest to get to 1,000 Rand. This one here only needs 3 years to get to 1,000 Rand. This one only needs 2 years to get to 1,000. This one needs 1 year to get to 1,000. So we notice that this is a geometric series, right, with a constant ratio of r, in this case 1 plus 0.1 to the negative 1, because each time you're going to be multiplying by that constant ratio to get to the next term. And this value, if you put into your calculator, this is going to be less than 1. Right? It's going to be 1.1 to the power negative 1. So if you do that on your calculator, 1.1 raised to the negative 1, you see you're going to get a value 0.9090, so on, so less than 1. So we're going to use the formula for a geometric series where your first term is this term here, 1,000 times 1 plus 0.1, the constant ratio being that value there, less than 1, and your n being 4 years. So we use that second geometric series formula, and we can just put in the amounts, and you can see immediately you're going to get the present value that you're actually going to need. 3,169 Rand 87 cents. That is the principal amounts that you deposit, so that you can assure that that money accrues interest over time while still taking money out. So using that now, we can generalize it. What we're going to do is we're going to call this present value P, the series of n regular payments, which we will call X, and are subject to an interest rate I. Okay, so from the given parameters, your first term is actually going to be the X times your 1 plus I to the negative 1, right? So that was this first term here. Then your constant ratio again is 1 plus the interest rate to the negative 1. Again, your R is going to be less than 1 here, and n payments. So if I substitute it into that formula, right, so it was the second one here, when R is less than 1, then if I simplify all the terms algebraically, right, so you're going to have your A term over there, you're going to have 1 minus your R term over here, and then 1 minus R over here. Essentially, you can bring this 1 plus I to the negative 1 down into the denominator, and then that can be distributed into each term here. So we get 1 plus I times 1, and then essentially we have 1 plus I times 1 plus I to the negative 1. Remember, that's a positive 1 there. So they have the same base. So you add the exponents, you get 0, which is just 1. So that's where that 1 comes from there. And then they add a minus sign in between. Cleaning all that up, you get the formula for present value. Now, look at the formula for present value annuities. The present value is the X, the regular payment you'll be making, times 1 minus 1 plus I to the negative n over I. Look how similar that is to the future value annuity formula. Okay, and that's X 1 plus I to the positive n minus 1 all over I. All right, so those are the two important formulae we're going to be working with, present value and future value. So let's have a look at an example with a present value annuity. So Shane wants to buy a home worth 8,500,000 Rand. He plans to sell his current home for 3.4 million Rand, which he will use as a deposit for the purchase of a new home. He secures a loan with AFK Bank, the repayment period of 10 years, and an interest rate of 9.5% compounded monthly. We want to calculate his monthly payments and determine how much interest he will have paid on his loan by the end of the 10 years. Okay, so the loan amount is that 8.5 million Rand, but he's sold his house for 3.4 million Rand. So essentially, he needs 5,100,000 Rand. That is our present value. That's what we want to borrow presently. The interest rate, 0.095 compounded monthly. So that means I is going to be 0.095 divided by 12. And N is 10 years times 12 months is 120 months. Okay, so we can work out the monthly payments X by using the present value annuity formula. Using a timeline, this is what it'll look like. He's essentially making the payments of X regularly 120 times, so it ends here at 119. Starts at T0. If you started at T1 and did T120 on your timeline, that's still correct as long as you have the right amount of X's he is paying, which is 120. I'm just assuming he's paying back at the start of the month. Or you could pay at the end of the month, T1, and then end at T120. From this timeline, again, 120 is your N. So if I use the formula now, and I rearrange for x, it becomes the present value times the interest rate all over 1 minus the 1 plus interest to the negative n. So using that, he has to pay 65,992 Rand and 75 cents for 120 months. That's 10 years of that amount to pay back the loan of 5,100,000 Rand. But if you take that amount, right, and you multiply it by the 120 payments, you see you're actually effectively paying back the bank nearly 8 million Rand. So if you take that amount you actually paid minus the amount you borrowed, you are actually paying 2.8 million Rands worth of interest alone. That is the interest that you are paying. Okay, so over the course of 10 years, Rashane will have paid an extra 2.8 million Rand on top of the original 5.1 million that he's paid back. Next, let us examine how to calculate how much money we still need to pay back the bank after a certain time period of paying regular installments. So this example basically tells us, as we're busy paying off a loan, we want to kind of figure out, well, after a certain time period, how much do I still owe off the loan? The reason why that's important to work out is because sometimes people will try to clear the loan in one go after a certain time period, and they want to know exactly how much that loan is still being outstanding. So let's have a look at this example. A school sells its old bus and uses the proceeds as a 15% deposit for the purchase of the new bus, which costs 330,000 Rand. To finance the balance of this purchase, the school takes out a loan that is subject to an interest rate of 9.5% compounded monthly, and the repayment period of the loan is 3 years. You want to calculate again the monthly repayments over these 3 years and determine the balance of the loan at the end of the first year, immediately after the 12th payment. Okay, so to calculate the monthly payments X, we establish the given information. Again, the school 15% deposit of the 330,000 Rand is calculated as follows. So the school essentially is putting down 49,500 Rand from selling their current bus. So the new bus, which is 330,000 Rand, minus the deposit that they make, that is the principal amount that the school wants to borrow from some bank. Again, we were given the interest rates compounded monthly, and because it's in months, 3 years is equivalent to 36 months. Now we can use the present value annuity formula to find that monthly payment, the X. So we can solve algebraically for X by rearranging, making X the subject of the equation, and we get 8,985 Rand 24 cents. So the school will need to pay back 8,985 Rand 24 cents per month for 36 months to repay the loan over that 3-year period. And lastly, if we want to determine the balance of the loan at the end of the first year, immediately after the 12th payment, we can actually approach this problem in 2 different ways, but they are both logically equivalent. The first approach is to calculate the balance of the loan at the end of the first year by determining the present value of the remaining 24 payments. So after the 12th payment, there's still 24 to make. So we can use the present value formula to determine how much is still left by putting in the deposits that we're making. But now we need 24 months left, and we see that we still owe 195,695 Rand and 12 cents. That is the first approach. The second approach is to calculate the balance by determining the accumulated amount of the loan for the first year. So essentially how much the loan is going to be, how much you need to pay off the loan for the first year, minus the future value of the first 12 payments. So after you paying 12 payments off. Okay, so the balance given by, so that is 280,500. That's how much you are borrowing. And that is going to accrue interest over 12 months, okay? Minus this amount you've been paying for 12 months. That'll give you the balance that's actually going to be left over after the 12 months. And you can see mathematically it works out to the same solution. So whenever you are trying to work out balance of a loan or some principal amount, what you need to do is either approach it in the first way by looking at the remaining payments and just simply using the present value annuity formula, or if you are lacking some information there, we can use how much the loan is worth in that time period minus how much you've paid off in that time period. All right, so quite a lot to unpack here. Make sure you go through each one carefully. We're going to practice some present value annuity problems. I'll see you in the next one.